Hello and welcome to the Cisco AI Insights Podcast, where every month we invite a technology or AI expert to the show to highlight and discuss trends, news, and academic papers from the worlds of AI, machine learning, and data science. I am one of your hosts, Rafael Herrera, and my co-host is a machine learning engineer and data scientist in Cisco's customer experience team, Sónia Marques. How's your day going?
Hi, Raf. All good.
This episode, we're hosting an AI approach showdown. We're comparing the big three of machine learning, and that includes traditional machine learning, deep learning, and large language models, which everybody obviously knows thanks to ChatGPT. But we're comparing them to see how they handle the messy, high dimensional reality of real world behavioral data. It's a study in fundamental trade offs, which include the statistical efficiency of traditional models, the temporal mastery of deep learning, and the semantic reasoning of LLMs. We're going to be asking which model architecture actually delivers the most reliable performance, and how do we tune them to find the signal within the noise of individual user data. To help us dissect these architectural differences and understand the future of model benchmarking, we are joined by a true expert in the field. She is one of Cisco's technical leaders in machine learning engineering and has dedicated her life to building robust, scalable AI systems that bridge the gap between raw data and actionable intelligence. Please welcome Leticia Fernandes. Welcome to the show, Leticia. How are you doing today?
Hey, Raf. Thank you for having me. It's a pleasure to be here today.
It's great to have you on board. Obviously, you're an expert. And because of that, I want to ask you first off, obviously, we're going to cover this paper, which you're going to be introducing in a minute. But before we jump into that, tell me, what are these three different approaches? Because I know them by name, but what do they each actually mean?
Okay. So we have machine learning, deep learning, and large language models being all these three different AI approaches being compared in the paper. The machine learning one, we can see it as the simplest AI approach that we can use for these sort of problems. Machine learning basically will find you the hidden patterns within the data in order to do either classification, regression, forecasting in this case. And it will basically require some feature engineering as well. So I think one of the limitations that we have comparing machine learning with deep learning is that in order for you to use machine learning, you need to have this prior work where you select your features, you do a lot of feature engineering in order for you to feed the right data into these models. They are easier and simpler to understand. So you have more explainability about what are these sort of models trying to do. For instance, we have a simple example of decision trees where we basically have these sub questions with a yes or no. So if you trace back the answer of a decision tree model, you can more easily understand why the model took that decision. As for deep learning, it is another level of complexity. So these models often behave a bit better compared with machine learning. Obviously, it will depend on the use case. And with deep learning, you don't really need to have all this work of doing feature engineering as an initial step, because deep learning, it uses artificial neural networks that will basically you feed your own data into these models, and it will be able to find out which features are relevant for the task that you're trying to do, either if it is detection, doing some sort of forecasting, etc. So depending on your task, the model can learn the features that are relevant for solving that problem and then execute the prediction that they have to do. As for large language models, these are models that are specific for text. So we need to remember that machine learning, deep learning, you can use mainly any sort of data. We may have time series, we may have text, sound, images. And for large language models, these models were trained, at least the text based ones, they were trained using text. So the beauty of these models is that they are very large and they are used for generation. So their main task is to be able to generate text, and you can prompt them with a specific task that you would like to solve, but it's all text to text based. Obviously, there are multimodal LLMs that take as input other sorts of data modalities, but in this case, and at least for this paper, we are using the traditional LLM model.
That really helps put everything into focus. Thank you very much, Leticia. I appreciate that. So let's jump into this paper that is actually comparing these three ways of doing things. Could you start off with the title, because it is probably the most epic sounding title I've ever heard. And tell us who actually made this research paper, too.
Yes. So this paper was made by some researchers from the Singapore University of Technology and Design. And the title of the paper is A Comparative Study of Traditional Machine Learning, Deep Learning, and Large Language Models for Mental Health Forecasting Using Smartphone Sensing Data. This means that we will be comparing these three different approaches for predicting the mental health state of an individual using the data from their smartphones.
You mentioned forecasting. So they're trying to predict the future state of an individual's mental state, right? It's different than the usual task of detection, which is more focused on the present state.
Exactly. So their goal, because we need to think about the motivation behind this paper, they want to be able to predict the mental health changes from individuals before the symptoms become apparent. So we don't want to be detecting when it's too late. We want to be able to predict when the mental health of an individual will be declining so that we can act on it sooner rather than later. So this task is mainly focused on forecasting, not detection. With forecasting, you're not, as you mentioned, Sonia, and very well, you're not doing the current prediction of the mental state as for now, but rather trying to predict how are you going to feel within 1 week or 2 weeks based on your behavior that you had until today. So this is the main focus. And for this particular paper, they are using data from 1 week in order to predict the mental health state at the end of the second week.
I think it would be interesting to first understand, before we go into the methodology that the authors used, to understand the data that is very broad and complex.
So let's start with the dataset. So they are using the college experience sensing dataset. This is a dataset that contains 5 years worth of data from 15 students. Something particularly interesting about this dataset is that it covers the pre-pandemic, pandemic, and post-pandemic times. So I think this will give us a bit more information about changes in behavior and mental health, because as we all know, with the lockdowns, we all had to pass through difficult times. And obviously, I think all of our behavioral patterns have changed. So it's interesting, at least they have evidence that something might have happened during that time in order to change the mental health of these individuals. What they are collecting here is smartphone centered data that basically they have this app within their smartphones. They don't have to do anything additional. So it will be a passive way of collecting the data. It collects information about your mobility, physical activity, sleep, phone usage, the communication patterns that you have. It's a way of collecting information without you really knowing that we are collecting these sort of patterns and that are very important for detecting these sort of behaviors. Prior studies have shown that changes in behavior can be directly related with several symptoms such as stress, anxiety, and depression. And these can be seen as differences in movement, communication that individuals have before they are consciously aware of them. The dataset will contain information from the sensory data that is being captured from smartphones, and they have self-reporting data. In order for us to have some sort of ground truth and to be sure about the mental health state of these individuals, they had to fill in some surveys weekly where we could extract the patient health through the patient health questionnaire severity level about their mental health state, which ranges from normal to severe. There are 4 targets in here for mental health states that they are having as ground truth for this dataset.
So once they got all this data, which they all consented to, by the way, I just want to make that clear to the listener. This wasn't a secret collection of their information. If you sign up for a study, you have to say it's okay. So once they got all of this data from these folks, what did they end up doing? How did they actually analyze something as complex as people's emotions based on simple things like movement and everything else like that?
This data set is composed about 172 different features. And something that they did originally was to select the most relevant features for the task that they are doing now, which is forecasting the mental health state. So they are using these 35 behavioral features that will basically give you some sort of signs of the mental health state of an individual. They are capturing that data throughout the period of 1 week. And then, using that data, they are going to predict what is the mental health state of that individual at the end of the second week. So, in order to do this, they have implemented these three different AI approaches. We have machine learning approaches that include logistic regression, support vector machines, we have decision trees. So, there is a lot of work going on in here. So, I won't go into too much detail into the approaches, but just for you to have an idea of the different techniques that were used. As for deep learning, we have other models that use the sequential and temporal dependencies of the data. We have temporal convolutional neural networks, long short-term memory and attention. We have transformer models as well being experimented during this study. And finally, we have the large language models. For the large language models, they mainly focused on the Quen 4 billion, 8 billion, and 14 billion parameters, and as well the GPT 4.1. So these three AI techniques with different models are the ones that they are using for these temporal tasks. Something that I found very interesting as well, because this is time series data. So it's numerical data, time series that is not directly processed by LLMs, because LLMs are expecting to have some sort of text as an input, even though the deep learning and machine learning approaches can more easily find the patterns and the signs within this data in order to make the prediction. For LLMs, we need to convert these numerical features into a structured text format. So what they did was renaming the features in a human readable term that LLMs can interpret. For instance, they have one of the features that they are capturing is the screen time that people spend on their phones. So in this case, we need to specify units. So we say this user spent 60 minutes screen on time, so that the model can more easily interpret these sort of variables. We also add the temporal ordering so that we know day one, these were the features, day two, we have a different set of features for the same individual, so that the LLM can also capture the temporal ordering of the data that we are feeding in. And finally, this is all structured in a way that is easier for the LLM to consume in order to make the prediction.
It's very interesting that they try to make the LLM consume these data in a different way. It's something that I haven't read a lot about, but it's quite interesting because the type of architecture that an LLM has, that is just predicting the next token, it's very hard for it to see such complex patterns that we assume there are in this data. Because, for example, usually, and this is me assuming some things, but I expect that a psychiatrist or a therapist is not able to look into such complex data about these smartphone devices and just infer. So this is not how the practice works. So it's not very reasonable even to ask an LLM, because of the way it works with text, to find these patterns that are so complex. So I really think, and I'm maybe getting a little ahead of myself, I think it really makes sense that the deep learning approaches worked so well. But Leticia, please tell us more about who shined, who shines in this paper.
Definitely. Yeah, you definitely don't want to spoil the ending of this story because it's definitely going to be a good one. It's okay, but I think you're right. I think what I found the most interesting about the study is that they're trying to make something so incredibly complex, which is human emotion, behavior, mental state. They're trying to convert that into data that something like this could even consume and interpret. That on its own seems like a huge feat. I don't know how they would actually be able to nail it on the first try. And I think we're going to see, again, more spoilers, that maybe they'll be able to get some information, but this is probably just the beginning. And I have a feeling we'll get there one day, but maybe these AIs will figure out how we're actually feeling. Just one question that I want you to consider and think about. which of these methods will actually be able to tell me that I'm happy? That's what I want to know. So let's continue on and tell me, what did we find?
About the results of this comparison, we have here, obviously, the listener is not seeing the results, but I'll try to describe them the best that I can.
And for any listeners that actually want to review the actual paper, I do add it to the description of every single podcast. So you can go ahead and download that and look at everything that we're talking about, because I know that saying numbers out loud, they can get lost in your mind and they don't always make sense. At least they don't for me. I don't know. Something's probably wrong with me. Maybe the AI will tell me. But we're just going to be talking generally and we'll throw a few numbers out there. If they don't make sense, it's okay. Just have a look at it on your own time. Okay.
Thank you, Raf. So,
Sure.
comparing machine learning, deep learning, and LLM approach. So, overall, the deep learning models are the ones that are achieving highest performance. We can see from the machine learning side that it provides good results when we are trying to predict if your behavior is normal or not normal. But in order to compare or to distinguish the mild, moderate, and severe cases, which are the abnormal mental health states, it struggles a bit more. And something that we also need to come back to is in terms of the data that we have. So this is a very unbalanced data set. We have around 62% of the samples are from the normal class. So machine learning without having proper balancing of the data might struggle a bit with this sort of data set. It's not a surprise that for the machine learning class, it's not performing so well on the abnormal classes. Now, comparing the deep learning approach with the LLM approach, LLM shows moderate performance, but with little performance difference. What does this mean? So we are comparing here 4 different LLMs, and the macro F1 score is very similar. So it almost doesn't change if we change the model that we are using for this prediction. And still, it has lower performance compared with the deep learning approach. We need to remember that by using these deep learning approaches, we are actually training a model using this data. So we are feeding examples of features from a normal behavior. These are the features from a severe behavior. So the deep learning approach is trained and fine-tuned using a very huge amount of data. As for the LLM approach, unless we do some further pre-training, which was not the case, we cannot directly or as accurately embed the knowledge from this domain-specific use case into an LLM. Obviously, they tried different approaches to overcome this because they were using some few-shot in-context learning where they feed some examples of normal behaviors and abnormal behaviors in order to improve the performance of the model. They also provide some statistical knowledge, such as some summaries of statistics of mean and variance of these behavioral features, so that the LLM has this context about what is normal, what is not normal, in order to make the prediction. But still, by using these adaptation strategies, it wasn't enough for the LLM approach to be better than deep learning. So in this case, deep learning approaches, and specifically the transformer model, was the model that was achieving the highest performance for doing this forecasting of mental health state.
You were mentioning the problem with data imbalance. That's very common, especially in the medical field. That the normal class, I know that normal in the context of mental health is not a great word, but let's say the baseline class is the most common. So there is a problem in here, and the authors also did some statistical analysis before they jumped into the methodology to understand the differences between the classes, and they found that the not normal classes were all very close together in terms of features. So, how would you say they dealt with it or not? What would you do instead, Leticia?
Yeah, I think something that I haven't seen is trying to balance a bit the data set, because they have tried a couple of things to overcome this by using the weighted cross entropy loss, which basically will assign higher weights to minority classes, and the focal loss, which will downweight easy examples and concentrate the training on these harder misclassified classes. But these are approaches that you can use within deep learning in order to solve or sort out this sort of class imbalance. But I think maybe doing a bit more preparation on the training data set, try to balance it a bit more before feeding to the model, that could be useful. I think this sort of studies would benefit from is not only giving the classification through this level of granularity, but also doing the classification if you're normal or don't have a normal behavior. That would be interesting to have as well. And I think they could more easily detect if there's an anomaly in the behavior than doing the actual classification through mild, moderate, or severe.
It would be a binary problem.
Yes, or anomaly detection, maybe.
Yeah, okay.
I think that could be explored because, regardless of the state, if you are having changes in your behavior that might influence your mental health, that's always valid to detect and to search for help. Because I think one of the benefits of these sort of problems is that you can use this information to detect before you're actually going to search for help. So I think it's interesting, regardless of being able to distinguish between the abnormal states. If you're able to detect that there is an anomaly in my behavior, that's very relevant.
It's essentially somebody saying, "Hey, are you doing okay?" If we can get to the point where an AI can just be like nudging you and be like, "Are you doing all right? Is everything okay?" There could be some value in that because if your feeling is, "No, I'm not actually feeling all right," then maybe that could be the first step to something else. Whether it is just knowing that maybe something is slightly off, or maybe it could be the first step to actually getting some kind of help. But we're not that kind of podcast. We're not going to provide any mental health advice, but there could be some value in this sort of study. So, disclaimer here, we are not mental health professionals.
A big research question that they also did in the paper about the personalization of these modeling strategies, because like we were saying, normal is not a good word in this context because there's no normal. Each one of us has a different baseline, and maybe that's worth looking into. So, Leticia, what did these authors explore in that area?
They tried a user agnostic mode and user aware mode. As you mentioned, Sonia, I think it's very important for us to have the background from the user when doing this sort of analysis, because the normal for me might not be the same as the normal for Raf. I'm an introvert, he's an extrovert, a clear extrovert. So obviously the communication patterns and all of that will be different. So if we compare my normal state with his normal state, probably his normal state will be abnormal for me. So something that they are trying to do in this case is to provide the behavioral features from the user into the model as well. So when we are trying to predict the model, the mental state of that individual, let's give a bit more context of what is the normality of this individual and the different mental states that they had during these last periods of weeks to understand the forecasting of the mental health state for that individual. And this actually provided very good results as well. We could see that, especially for the deep learning approaches, which were the ones that achieved higher performance, that we had a lot of improvements by using these personalization attempt of giving the user behavioral features into the model. For the machine learning one, we can also see that there was some improvement. It was moderate, it was not as high as for the deep learning, but still there was some improvement on providing these personalization as input. As for the large language models, surprisingly, it wasn't very effective. It could even be more inefficient if we provided the information from the user as input.
See, now that I actually found a little bit surprising because all I hear about are LLMs. LLMs are the solution to and cause of all of life's problems. So, why is it that LLMs were not actually able to do this? Why is it that LLMs are not the ones that are finding all the answers here for us?
I really think this ties with what we were mentioning before about the difficulty of LLM understanding really complex patterns in the input data. In the paper, there is not a lot of detail on the methodology, but I'm assuming that it would almost be like a multi-model approach to this LLM, because just feeding text wouldn't make sense to expect that the LLM would find these such complex patterns. So I think it makes sense that when adding even more specific information about a specific individual would just make no difference necessarily, or maybe just confuse even more. So that is my take, but it's not something that is really answered in the paper, I think.
Yeah, and I also think because we need to remember the type of LLMs that they were using in here. They were relying on Quen 3 with 4 billion, 8 billion, 14 billion parameters. They also tried with GPT 4.1. But I think today we have higher performing models that could probably work a bit better for this sort of task. And also, it will depend on how they prompted the model. All the prompting engineering is a science on its own. So, if we don't get the data right into the model, that might be one of the reasons why it's not capturing what we want. Because I feel that if we give enough examples, if we explain the task properly, it should be retrieving a bit better results, even though I must say that I always think that fine-tuning a more traditional model will always perform a bit better, but at least if we want to have, so the benefits of having LLMs is if you want to have some prototype faster, it will give you what you need. But if you're expecting to have higher performance, then might not be the ideal.
So it sounds like the more personalized approach of deep learning was the biggest winner in all of this.
Yes, that's correct.
I think that this is very complex. They're trying to answer a lot of questions. I think that is why we have so many that are a little bit open ended. So I think that just this personalization bit could be a paper by itself because there's so much to explore. I'm really interested in actually looking into other papers that use this data set because this is 5 years of data even with the pre and post pandemic information. I think there's a lot of potential to dig into this. I think it was a really cool read. Thank you, Leticia, for sharing this with us.
Oh, you're welcome. I hope we all learned something from this because it was a very interesting paper. Connecting AI with healthcare is always something interesting.
This is essentially an exploratory research paper, but I think the hardest task in all of this is forecasting based off of data from one week to another. Hey, maybe I was moving that week and I'm pretty stressed out about it. Or maybe my pet fish died and I'm just a little bit bummed out about that and the baseline was set wrong. Who knows? There's a lot to look into with things like this, and I think adding more context to it would help. Unfortunately, that's where the challenge for the LLMs is. So we'll see where it goes from there. And maybe it is just going to be a full dedication to deep learning on a very personalized, person to person basis. Who knows? It's a lot like activity tracking with your Apple Watch and things like that. Eventually, it gets to know you and it knows when you're being lazy. Fingers crossed that we can get to that point where we can get more data reflecting back at us and maybe helping us out in the end. Leticia, thank you so much for bringing this paper to our attention and everyone else that's listening out there in the world. Thank you for listening to the show. And if you like conversations with experts about AI, machine learning, and all the other emerging data science technologies rapidly shaping our world, please subscribe to the feed wherever you might get this podcast. We are releasing these monthly and would love to have you along for the ride. So until next month, I am Rafael, I've got Sónia, and we have Leticia here. Thank you for listening, and we'll catch you next time. Bye bye.
Bye.